So let's talk about carboxylic acid. Carboxylic acid is the most acidic organic functional group. And we've said that the pKa of the carboxylic acid proton is around 5, but there's a lot of variation on the pKa of the carboxylic acid depending on what this is. So, for example, if R is a trifluoromethyl group, I think that's right. The pKa is 0.36. There's a table that you'll want to know about in the beginning of chapter 19 that has the pKa of a bunch of these carboxylic acid derivatives. It's table 19.3 on page 865. 0.23 is the pKa for that. I say that was 865. So you'll notice that if you put electronegative elements, if we draw bond dipoles for this, we've got 3 electronegative groups that are pulling electron density away. This is an inductive effect. And inductively electron withdrawing groups will change that acidity. This is comparable to mineral acids, right? It's an organic acid, but it's much more acidic than most organic acids. Oxalic acid is another example, which is 1,2-ethane dioic acid. That's a diprotic acid. And if you look in the table, pKa1 for oxalic acid is 1.27. And pKa2 is 4.19.
Why is it
So
different?
because we have this electron withdrawing carbonyl group adjacent, the first acidity is greatly enhanced. You'll notice that the second acid dissociation constant is always less because you'd be making a dianion, right? The first one always comes off much more readily. But you'll also notice if you look at the rest of the ones in that table, that if you move to succinic acid, or acetic acid in this case, right, if you put a bunch of CH2 groups between those, the difference between pKa1 and pKa2 goes down. It doesn't matter which side you decide is 1 and which side you decide is 2. Because the anion this negative charge is much further away from where the new negative charge would be if you take that hydrogen off, it affects it less. Right? In this case, the negative charge from taking the first hydrogen off is really close to the negative charge from the second one. So the further apart you get, the more they both coalesce to the standard kind of 5-ish pKa that you would normally expect. You'll notice if you look at the rest of the series from oxalic acid to malonic acid and succinic acid and valeric acid, you'll find that the pKa values gradually get closer together. pKa1 gradually rises. because the carbonyl group that's pulling electron density away and increasing its acidity gradually gets further away, and pKa2 becomes closer to pKa1 because the two carboxylic acids are acting more independently when they're further apart. So one thing to know about carboxylic acids is that they're acids, right? And they're called carboxylic acids, so it's hard to forget that. The other thing you need to know about carboxylic acids is this is about the most oxidized functional group you can get. Which means it takes priority over all functional groups in naming. Right? It's carbon in its highest positive oxidation state, where you've removed a lot of electrons by attaching it to electronegative oxygen, so you're going to hog that. So if a molecule of carboxylic acid is always named as a carboxylic acid, whereas if a molecule is a ketone, right, it's higher priority than alcohols or alkyl halides or alkenes, but it's lower priority than the carboxylic acid derivatives, because the most oxidized carbon always takes the priority for naming. So we need to understand that. We also need to understand, though, that carboxylic acids, even though they're acids, are amphoteric. It's possible to protonate carboxylic acids, and many of the reactions of carboxylic acids go through that protonated form. It's not a great equilibrium. But you know there's a minor resonance structure that looks like this. And in that minor resonance structure, this oxygen looks like it has a significant partial negative charge on it. So it would be reasonable to protonate it. My arrow pointing in the wrong place. You should start at the one. Right, that's got a resonance structure. Actually, it's got a couple of resonance structures. Because you've got this OH group as well. So it's a resonance stabilized cation, which means it's going to be reasonably stable. The pKa of this protonated carboxylic acid is typically around -6. pKa of this is typically around -2. So the equilibrium constant for this reaction isn't going to be very favorable. And we could illustrate that by showing a really small line going forward. In fact, you can tell me what the equilibrium constant for that reaction is.
10 to the -4?
About 10 to the -4. Which means normally in the reverse reaction, since it's larger than 10 to the third, we would say it goes to completion, which would mean we'd say there basically isn't any of that. But lots and lots of reactions with carboxylic acid derivatives involve first protonating it and then subjecting this carbon, which now has a partial positive charge, that you can see in the minor resonance structure, to nucleophilic attack. So there are tons of nucleophilic acyl substitution reactions that depend on the fact that even though that equilibrium is not very favorable, it happens anyway. So you frequently have some of this in solution that can drive a reaction forward. So most of the time, carboxylic acids are going to lose their proton, but if you put them in the presence of strong acids, right, and any strong acid in water is going to give you hydronium, you're going to get the protonated form, which can then lead to further reactions. So normally, the way this textbook is set up, the first thing we do when we introduce a new functional group is we review the ways we already know for how to make that functional group from other functional groups. That's what we did with aldehydes and ketones. Let's do it for carboxylic acid. So now you actually have to participate, because because you already know a bunch of different ways that you can make carboxylic acids. And so I don't have to tell you how to make carboxylic acids. You can tell me how to make carboxylic acids. So what functional groups do you know already that can be converted to carboxylic acid? And it's actually most of the same suspects that can be made into aldehydes and ketones just by changing the conditions slightly.
You can do a primary alcohol with K2CR2O7.
So chromium-6 reagents in aqueous acid.
Yeah.
This is over-oxidation. But if what you want is the carboxylic acid, it's not over-oxidation, it's exactly the oxidation you're looking for. There are various forms of chromium-6. It doesn't have to be only water. You can actually have some acetone co-solvent in there, in which case it's called the Jones oxidation. But that is going to form the carboxylic acid. And chromium-3. Chromium-3 in solution is green, chromium-6 in solution is orange. So the reaction even kind of tells you when it's done by turning from orange to green. It doesn't have to be K2CR2O7. It could be CrO3, which is another form of chromium-6. And both of these, when dissolved in aqueous acid, become H2CrO4, which is the chromium analog of sulfuric acid. So what actually does the oxidizing is chromic acid. It's a strong acid. It's not one of the 7 common strong acids, but it's a strong acid, and it will do the oxidation. Are primary alcohols the only functional group that can be oxidized to carboxylic acids with chromium-6?
No.
No.
I was just thinking for the that particular reagent with over-oxidation.
So aldehydes, because they're intermediate in the formation of the carboxylic acid by over-oxidation, can also be oxidized to carboxylic acids. And it's not limited because the aldehyde is more easily oxidized than the primary alcohol. Aldehydes can also be oxidized with nitric acid, which is nitrogen in the +5 oxidation state, which is a high oxidation state for nitrogen. And since nitric acid is incredibly cheap, it's formed in large quantities from the Ostwald process. If you're doing this on an industrial scale, nitric acid is a preferred reagent versus chromium-6. Plus chromium is toxic, it's hard to dispose of, and chromium mixed with organics is really toxic, so no waste company wants to take mixtures of chromium and organics. So nitric acid is much safer, right? There's lots of nitrogen in the atmosphere. The byproducts of nitric acid oxidation are less toxic, right? So this is oxidation. We can oxidize a less oxidized functional group, like an alcohol or an aldehyde, to the carboxylic acid using metals in high oxidation states or non-metals in high oxidation states. You can do this with potassium permanganate. And sometimes that's a good method, but it often gives byproducts. With primary alcohols, it tends to chew things up. Manganese 7 is too powerful an oxidizing agent for most doses. Right? So primary alcohols and aldehydes can be converted to carboxylic acid. That's one method. How else do we know to make carboxylic acids? What other functional groups can be converted to carboxylic acid? While manganate is up there, there's another functional group that uses potassium permanganate productively to generate carboxylic acids.
alkyl groups?
And that's alkyl groups attached to an aromatic ring. So if you have an aromatic, an alkyl benzene, and you treat that with KMNO4, you will oxidize out alkyl group right off and convert it to the carboxylic acid. Right, so we're going to chop off the carbons. KMNO4 won't react with ordinary alkyl groups, only alkyl groups that are attached to aromatic ring. So you can make benzoic acid. This is terephthalic acid. But you can do it with any alkyl benzene with other substituents to make a benzoic acid.
How do we decide like where to cut it off? Is it always just like going to be one carbon so it can be the carboxylic acid? So even if it was like a whole bunch more?
Yeah, how do you decide where to cut it? You always cut it between the alpha carbon, the one that's attached to the benzene ring, and all the others.
Okay, thank you.
Right? It chops off all but one carbon, and that one carbon is
Gotcha.
converted to benzoic acid.
Okay.
So that's another oxidation, right? This is oxidation of alkyl acids. Because the carboxylic acid is the most oxidized functional group, it probably was intuitively fairly obvious that you're going to oxidize other things. So those are not the only two functional groups that can be oxidized in carboxylic acid.
What about like the allylic position? Is that possible?
The allylic position can be oxidized if it's an aldehyde, like an allylic aldehyde or an allylic alcohol.
Okay.
If it's primary, it can be oxidized using these same methods.
Mm-hmm.
But there's no special allylic oxidation. That manganese dioxide converts the allylic things to ketones and aldehydes, not carboxylic acids. So it's not really a subset of this. Right. Oxidation of this benzoic position is special, but oxidation of the allylic positions. But there's another functional group that we can oxidize that we can make carboxylic acids out of. We can also make aldehydes and ketones out of it by simply changing the workup step.
Oh, it's the ozone. Is that a thing? Osmosis? When you, yeah, the cleavage.
So if we do oxidative cleavages of alkenes with an oxidative workup, instead of the standard mildly reducing workup, I'm just going to leave our primes out there. So ozone and dichloromethane, one followed by hydrogen peroxide. If it's disubstituted on the end, it forms the ketone. But if it were a monosubstituted alkene, it forms the carboxylic acid, hydrogen peroxide. Goes through the ozonide. So we still have standard ozonide. But then when you work it up with hydrogen peroxide, instead of removing one of those oxygens, all of those oxygens stay in place and you end up with carboxylic acid from the side that had the hydrogen. Right? Gotta have a hydrogen. If you don't have a hydrogen there, you have ketones, no matter what. So those are some standard methods. These are methods you already know about. And this one is not actually included in chapter 19 in the summary of methods. And all of these are oxidations. So the next question is, are there ways to make carboxylic acids that you already know about that are not oxidations? And the answer should be yes. There should be one reaction that you know at least to make carboxylic acids that are not oxidations. That's from chapter 9. And it was important in preparing alcohols from alkyl halides without having to worry about carbocation rearrangement. And it's a hydrolysis of a carboxylic acid derivative. There are lots of different carboxylic acid derivatives, and almost all of them can be converted to carboxylic acid by hydrolysis. The one that I think you should know about is called saponification. And saponification converts to ester to carboxylic acid. And you should know the mechanism of that reaction. So if we start with ethyl benzoate, for example, and treat this with NaOH, KOH, and then later with aqueous acid, we're going to break this bond. Hydroxide ion attacks. And that's a reversible step one, that's the nucleophilic attack. And then we have a loss of the leaving group, take out ethoxide. Which is a really unfavorable reaction, because alkoxide ions are terrible leaving groups. But we got it to go anyway by promising the alkoxide ion, by sweet talking it and saying, I know you don't want to leave, I know you're a strong base, but if you leave, I'll give you a proton in the next step. Look at this nice proton that you can have. Wouldn't you really like to leave so you can have that proton? So we covered it last semester in the context of alcohol synthesis from esters by hydrolysis of the ester to produce the alcohol. But if we then protonate that fourth step with strong aqueous acid, the carboxylic acid can also be formed from that. So this is another proton transfer step where hydronium ion is going to donate hydrogen. And the equilibrium constant for that is also quite favorable, about 10 to the third, is this, or 10 to the fifth rather. 10 to the 7, because that pKa is about 5-ish, and that pKa is about minus 2-ish. So the difference between those two is about 7. Right? So we know that this one's about 10 to the 10th. Because the pKa of the alcohol proton is 15, and the pKa of the carboxylic acid proton is 5, so that's 10 orders of magnitude different. So I've drawn those 3 and 4, which are proton transfer steps, as one way, because both of those have equilibrium constants that are huge. So saponification of esters to carboxylic acids, but that's not the only carboxylic acid derivative that we've seen. You can also hydrolyze nitriles. And it can be done in strong base or strong acid, usually with heat. And that's actually true of most of the carboxylic acid derivatives. Either strong aqueous acid or strong aqueous base will convert pretty much any carboxylic acid derivative to carboxylic acid by hydrolysis. The full mechanism for this hydrolysis of the nitrile is actually in one of the pre-recorded videos. It's a lot of steps. I'm not going to go through it. It's covered towards the tail end of chapter 20. So hydrolysis of carboxylic acid derivatives, esters, nitriles, amides can be converted using exactly the same condition. And I'm using a benzene ring here just for convenience. But they can be converted as well. And in both acid and base. The mechanism for base-catalyzed hydrolysis of an amide is exactly the same as the mechanism for base-catalyzed hydrolysis of an ester, with the difference that the leaving group is even worse. Because in this case, the leaving group will be NH2 minus, right? And ammonia has a pK of 35. So the equilibrium constant for that last step is now going to be ridiculous. Amide ion really doesn't want to leave. But anybody can be convinced to leave if you promise them a nice juicy proton in the next step. But leave now and you can become a proton to be neutral. And they love it. So hydrolysis of carboxylic acid derivatives is another important way to make carboxylic acids. And then the other method that's talked about, which I don't think you've seen before. What are we on, 5? Carbonation of organometallics. With CO2. Often CO2 solid as dry ice, but it could also be CO2 gas plus pressure. And since CO2 is a gas, we can force that reaction forward by applying pressure so that the pressure is relieved as the CO2 gas is consumed. And the Chapter's principle works in our favor. And since organometallics come from alkyl halides, we can convert alkyl halides into carboxylic acid derivatives. By first forming the organometallic, and then adding dry ice. Almost all of these reactions to form carboxylic acid will have a final step of an acid workup because the carboxylic salts are pretty stable, so the acid workup will be necessary protonated. So that's a nucleophile basal addition reaction. Whereas the method we just talked about prior, which is the hydrolysis of the carboxylic acid derivatives, those are nucleophile basal substitution reactions. Aqueous acid is going to protonate that to get the carboxylic acid. doing a nucleophilic attack followed by protonation. Class A. Nucleophilic basal addition. There's actually a special case of this that works on phenols. And we'll put a carboxylic acid derivative carboxylic acid rather adjacent to the OH group of the phenol. This is the Colby reaction, and it's hiding on page 1027. Actually, inside one of the chapter exercises. This is chapter exercise 22-19. Colby reaction is hiding there. And we need to make carboxylic acids from phenols using a fairly mild base and exploiting the fact that the pK of the phenol hydrogen is about 10, which is 5 orders of magnitude more acidic than standard alcohol. So you can deprotonate that pretty readily using a mild base. Form the phenoxide ion. And what does that phenoxide ion look like to you? At least studied. It looks like an enolate. Phenol is in fact an enol, right? It's stable in the enol form because the benzene ring has special stability, but this is basically an enolate ion. And you know that enolate ions react with carbonyl compounds. So I'm going to redraw it so that enolate is on the other side. And carbon dioxide is basically a carbonyl compound. So this is an alcohol. Effectively, right? Enolate formation in step 1, deformation, but that of course is not really enolate. Followed by nucleophilic addition in step 2. And then we've got carbonic acid. Protonate this guy. Let's see the proton transfer. And then we can remove this proton form the enolate, basically. And that regenerates the aromatic ring. Why it likes to happen. Because the carboxylic acid proton is much more acidic than the phenol proton, and because that's a 6-membered ring transition state, product of the Colby reaction will actually be a carboxylated salt, so you can make this acid work on. Whatever. Alkaline method. Right? So the Colby reaction is basically an alcohol condensation, or an alcohol addition, rather, sorry, not an alcohol condensation, because we don't get an alkane unsaturated carbonyl compound. So enolate formation, alcohol addition, and then a proton transfer step to regenerate the aromatic ring. The carboxylic acid adds to the position on the benzene ring that's next to the phenol. So it's an ortho substitution where we have the hydroxy group and carboxylic acid by adjacent positions. And it's pretty mild because bicarbonate is not a very strong base. So that's a summary of ways to make carboxylic acids. What do you think the quiz is going to be on Tuesday? Reactions, mechanism,
quiz?
or synthesis?
I think it's going to be reactions.
Probably reactions.
So wait.
I might throw you a curve and combine reactions and then a mechanism on the tail end.
Oh.
Go ahead.
So that the thing at the top, would we protonate that to get our desired final product?
Yep, acid workup.
The circled one?
Yep.
Okay.
There's almost always a mild acid workup, ammonium chloride or like 1 molar HCl, because the initial product of almost all of these reactions is oxalate salt, especially if you're in base, right? If you're doing an acid catalyzed cleavage with a carboxylic acid derivative, you'll get the carboxylic acid derivative. But if you're doing a base catalyzed reaction, not so much. So you would probably suspect the reactions quiz with maybe a mechanism, because you should know the mechanism of quantification, and you should know the alcohol condensation, various mechanisms in there. It's a little late to be taking a break since it's like 17 minutes before the end of class. So what I'm going to do is just tell you one more thing, and then we'll just break early and end class at 10 instead of an after. Sorry, I didn't give you a break. I got too excited. The reaction mechanism that carboxylic acids and carboxylic acid derivatives undergo is nucleophile basal substitution. So the difference between carbonyl groups, where we have hydrogen or carbon here, and carboxyl groups, carboxyl groups have an electronegative element with a lone pair. Attached in place of one of those hydrogens or carbons. And that's what causes them to undergo nucleophilic acyl substitutions instead of nucleophilic acyl. Because all of these groups, because they have an electronegative element like that, are potential leading groups. Since they're electronegative elements, they're somewhat able to stabilize a negative charge, which means that they can leave, whereas carbon anions or hydrogen anions are not going to leave. Those are just too strong of bases to be kicked out as a leaving group, but any of these electronegative elements can. So every carboxylic acid derivative, and again, let's just use benzene as our one side, and then we've got something with a lone pair on here. And there's a leaving group with a lone pair. I'm going to illustrate it with the thioester, just because we haven't seen the thioester before. Every one of these derivatives can undergo a reaction with a nucleophile, where we get a nucleophilic attack. And then a loss of the leaving group. And that two-step process of nucleophilic attack, followed by loss of leaving group, is the nucleophilic acyl substitution. The first step is the same as the first step of the nucleophilic acyl addition. It's a nucleophile attacking the positively polarized carbonyl carbon. The difference is when we have something that has the potential to act as a leaving group because the electronegative element can stabilize the minus charge, instead of protonating the alkoxide, it comes back in, reforms the carbonyl group, and kicks off the leaving group. So we do a substitution instead of a addition. It's not an SN2 substitution, or you can't do SN2 substitutions, nucleophilic alkyl substitutions at sp2 hybridized carbon, only sp3. So you have to form this intermediate that has the tetrahedral carbon. And that makes sense because the lowest unoccupied orbital that the nucleophile is going to be donating its electrons in is the pi star orbital. So we break the pi bond, not the sigma bond when we donate. If it's a negatively charged nucleophile, then we're done. Right? Because this product will now be neutral. If it's not, if it's a neutral nucleophile, then generally it's not going to be a good enough nucleophile to attack the unprotonated carbonyl, and we're going to have to protonate the carbonyl first. Right? So if the nucleophile is neutral, we often have a protonation of carbonyl carboxyl. And that's called the Fischer esterification, or one example of that is the Fischer esterification. If you're in group A, you've already done a Fischer esterification to make your unknown alcohol into the acetate ester with acetic acid and catalytic sulfuric acid. That's a more complicated mechanism. That was actually 6 steps. I'm not going to show it to you today. But on next Tuesday's class, it says nucleophilic acyl substitution. Don't miss this one. We're going to do the acid catalyzed nucleophilic acyl substitution and the Fischer esterification mechanism on Tuesday. And then any guesses as to what the quiz is going to be next Thursday?
That mechanism.
The mechanism of the Fischer esterification, right? Which is also the mechanism you're allowed to put in your notebook at the tail end of the unknown alcohol to ester lab. So we're going to get you ready for your lab notebook check at the same time. How reactive these are towards this nucleophile fissile substitution, which is on the syllabus for today, but we're actually going to do that on Tuesday, depends both on how good a leaving group it is. Right? The better the leaving group, the better this step. But it also depends on to what degree this heteroatom here stabilizes or destabilizes the partial positive charge on carbon, and that affects the rate of step 1. The more partial positive charge we have on the carbonyl carbon, the faster step 1 goes. The better the leaving group, the faster step 2 goes. So there's going to be that kind of interplay between how it interacts with the carbonyl carbon in the starting material and how good an anion it is when it leaves. So we'll talk about those on Tuesday. We're going to quit 10 minutes early today since I didn't give you a break. You get your 10-minute break now. And that'll help Emma because she's got an exam in 20 minutes. So I didn't do that on purpose. It just worked out that way. Any questions? I covered a lot, but hopefully some of it was reviewed.